Good morning. Welcome everyone to the 7th Annual Family Literacy Day here at the Montreal Children's Hospital. My name is Caroline Erdis. I'm a speech-language pathologist here at the Children's, and for the past few years I've had the pleasure of championing the Lire, Imagine, Read literacy project. Lire would like to invite you to join us in the 2B area of the hospital after this lecture, where we have information kiosks set up, and you can meet some of our community partners and obtain information about literacy for yourselves and for your families. You will also have a chance to enter a contest for chapters gift certificates and an e-reader, and of course we have free coffee and cookies. I also want to let you know that our guest speaker, Dr. Pugh, has kindly agreed to also give a public lecture tonight at 7:30 here in the amphitheater. And so if you know anyone who has not heard about this, please do inform them. It's open to everyone. I'd like now to introduce you to Dr. Kenneth Pugh. It's an absolute pleasure for me to introduce him because in the world of reading disabilities, he really is a rock star. Dr. Pugh is President and Director of Research at Haskins Laboratories, a Yale University and University of Connecticut affiliated institute that's dedicated to the investigation of the biological basis of language. He holds academic appointments as professor in the Department of Psychology at the University of Connecticut, as an associate professor in the Department of Linguistics at Yale University, and as an associate professor in the Department of Diagnostic Radiology at the Yale University School of Medicine. Dr. Pugh also directs the Yale Reading Center. He is a member of the Scientific Advisory Board of the International Dyslexia Association, a corresponding member of the Rodin Remediation Academy in Stockholm, and he served for 4 years as a member of the Language and Communication Studies section at the National Institutes of Health. Dr. Pugh recently served as a member of the Committee on the Learning Sciences, Foundations and Applications for Adult and Adolescent Literacy at the National Research Council of the National Academies. His research falls primarily into 2 broad domains, cognitive neuroscience and psycholinguistics. And a fundamental interest of his continues to be research into the neurobiology of typical and atypical language and reading development in children. Welcome, Dr. Pugh.
Thank you very much. Good morning, everybody. So I'm very happy to be here. Thank you for the invitation. I look forward to spending the day meeting with various groups of people who are doing work that is near and dear to me, the study of reading. Reading is an interesting phenomenon. It's an interesting thing. It's an amazing exercise in plasticity for the brain to build this ability to take print, to take vision and translate it into language in a way that has to be fast and automatic. We'll talk about that in a minute. But if you can read, you can open the world of knowledge. I do a lot of grants, NIH projects that involve looking at reading and how it comes online in children in many languages around the world. And we do work in Taiwan. This is my favorite Taiwan temple because this god is showing you what a real reader does. He extracts the knowledge of the world from print. But look at his eyes and look at his concentration. You need attention, you need to understand the code, and you need to be able to be fast in order to be able to process the story. So this is Grand Rounds, and so this talk will be more technical, but I'll be covering a lot in this session. So I'm going to really breeze through a lot of data. But my job, if I do it right, is to give you a big picture sense of why, in particular, modern neuroimaging can provide value added in understanding typical and atypical reading above and beyond cognitive behavioral testing, which does a terrific job and tells us a lot. So what is it that neurobiology provides in understanding individual differences and struggles? And what do we currently know? And most important, given all the hype and hooey that is often surrounds the kinds of studies we do with pretty pictures of the brain, which can be meaningless if they're not good science. Just because it's got a brain doesn't make it good science, as you all know. And so my job as well is to give you a sense of both the promise of neuroimaging, where it can take us, and its limitations. Let's just start with the obvious and important issues. Reading is important. If you cannot read, you cannot succeed in the modern world. And significant numbers of children in all languages and cultures will fail to obtain adequate literacy skills. In some, even in my country, in the United States, in many states, up to 40 to 60% of kids are not reading at grade level. And it's actually worse. And I'm involved in a project in the developing world right now where you have poverty, early childhood stress, nutrition, environment driving very high rates of illiteracy or limited literacy outcome. And so this is a public health and a medical issue, obviously, because if you cannot become an automatic reader, the modern world does not have a place for you. And so I was involved in the Connecticut longitudinal study at Yale for many years, designing cognitive and neuroimaging experiments for it. And one of the major outcomes of that well-known study is that the life, socioeconomic, educational, and mental health outcomes of kids who are struggling with reading early on and don't remediate are not good. And so I'm happy to take questions on what that means technically. But if you don't remediate reading early on, the adult outcomes at every level, on average, are not good. And for many kids around the world who fail to acquire adequate literacy, the cause is obvious: a lack of opportunity, or because reading is not simple, and because we're not wired for it. It can be taught really stupidly. And when it's taught stupidly, you also get bad outcomes. But for a significant number of kids who have good opportunity and good teaching, reading fails to come online. And these are kids we define as reading disabled, dyslexic by some terms, or challenged to literacy. And these are the kids that I've studied a lot over the years using gene-brain behavior approaches. So a little bit on reading. Give me a second to give you a little feeling for the job of what it means to read. First of all, what a skilled reader needs to be able to do is to get from I, when the printed word hits the retina, to the meaning as fast as bloody possible. Because if you cannot decode a word and pull it off the page in about 250 milliseconds and change, you are not going to be able to read sentences and understand what the author is trying to tell you, because by the time you get to the end of the sentence, you're going to forget the beginning. So there's sort of two ways of thinking about reading. There is the skill of reading, which is learning to translate vision into language bloody fast and automatically. And then there's comprehension and strategies for comprehension and reading for meaning. And that's what follows. And significant numbers of kids who present with reading disability have problems with the first one. Decoding never becomes automatic. And many kids in 4th grade and on begin to present with other problems, which I will not go into today, but they're important. This is called late emerging reading problems, and they often show up in the domain of comprehension. But today I'm going to focus on dyslexia, essentially, which is the problem of being able to pull the word off the page in 250 milliseconds and change. Okay, and if you can't do that, there are major limitations on what you can do. Skilled readers can read words in alphabetic languages, can read words really fast. And interestingly, if you know how to read well, you can look at something that you've never seen before, a pseudo word, and you can read it almost as fast. So if I have an experiment where you see the word and you speak into a microphone, you simply name it. If it takes 250 milliseconds to kind of get to the meaning and another 250 milliseconds to get it out the mouth and into the microphone, so about 500 milliseconds to name real words. If I give you something called a sight word, which is a word that you've seen a million times, will you be faster at saying it into the microphone than a nonsense word you've never seen? Yes. How much faster? If I match the stimuli, 30, 40, 50 milliseconds. So if you're a skilled reader, you can decode nonsense words almost as fast as real words. And that's important, because that's what needs to be built into the brain in order to become able to pull the text off the page and think about what the author is trying to tell you. A key concept in all of this is that the development of skilled reading depends on establishing efficient connections between graphemes, phonemes, and meaning. Just to illustrate this briefly, this is a whole lecture in and of itself, especially for a pocket protector word recognition guy like me. This is what, when a child learns to read, if they've been in an adequate and a stimulative environment, they will know many thousands of words, maybe 20,000 words to ear. So they have semantics, meaning, and phonology. What they don't have is the other element in this triangle, the link between some way of representing phonology visually. So in an alphabetic language, of course, it's consonants, vowels, letters. In a syllabic language like Hangul Korean, it's syllables. In Hindi, it's alpha syllables. And in Chinese, it's a bit more opaque and has to do with representing certain sound patterns and meaning patterns in what are called radicals. In all languages, however, what you're trying to do is take spoken words and represent them by some visual unit. And when you learn to read, you don't have this left base of the triangle, but you need to get it. And in order to become a 250 millisecond guy or gal who can decode instantaneously, you need to bind orthography, the representation of letters, phonology, and semantics, and it needs to become overlearned and fully resonant. So that's why the arrows go in both directions. This is the cognitive piece. We're going to map it into the brain as we go forward. But it's meaningless to look at neurobiological circuits if you don't know what's going on cognitively, frankly. That's where we get into trouble. People say, I'm going to study reading, so lie in a magnet and read, and we'll map the brain. Well, guess what? The whole brain is active when you do anything. So if we're going to understand reading at a neurobiologic level, we need to understand what the cognitive challenge is. The cognitive challenge is to build this triangle, and to build it in such a way that you reorganize language cortex, as you'll see in a few minutes, and make it able to tolerate visual input. And the most prevalent set of features for children who present with reading disability are as follows. Word recognition in languages like English is slow, painfully slow in many cases for kids. These bright, beautiful kids who are otherwise normal and who look at print and just break your heart, pulling the print off the page. Slow. Labored, which means not automatic, so very attentionally demanding, never efficient. And in languages like English, which is an irregular orthography because it's got words like pint that should be pint. Unlike Spanish or Finnish, I do a lot of work in Finland, where the languages are very transparent. If you know how it looks, you know how it sounds. So in English, dyslexic kids present at rates of about 10%. And they are slow, labored, and error-prone. In languages like Finnish, they present, Finnish is an easy language to read. Every letter has only one sound, and every sound has only one letter. Of course, the words go on like 5 pages, but that's a whole other, that's morphology. I still can't figure out Finnish, it's killing me. Plus the winters are killing me as well. You think Montreal's bad, forget about Jyväskylä. But here's the deal. In Finland, you get about the same percent if you measure fluency. But kids are slow, labored, not automatic, but not error-prone, because you don't make errors in an easy language, but they look the same. And when you look at the brain, as you'll see, and we see the failure to develop these reorganized speech systems that become able to tolerate print, it does not become automatic. What predicts this? Well, I'm going to present this very quickly. Many people here know, and many of you don't know, a lot about reading, but I will give you a very important, simple element. And I take some pride, not personally, but institutionally, Haskins Laboratories, which is a very famous and historic speech, language, and reading research institute, 77 years old. The great discovery in the 60s was the importance of phonological abilities in learning to read and in reading failure. So when you're building that triangle, you need to reorganize your brain in such a way that you can represent the parts of words by letters. You need to make these connections. And the single best predictor of risk for reading problems in kindergarten before formal instruction is the ability to understand that spoken words are made of pieces. This is called phonological awareness. And it's often measured by tasks like this. Say the word cat without the first sound, and you say at. It's called elision. It's a very, very good predictor. So at the time when Haskins researchers Liberman and Shankweiler began this work, the going currency was reading's visual, therefore reading problems are probably visual, flipping the letters and such. The data has not been kind to that theory over the years. That doesn't mean children with visual problems won't struggle with reading. But the vast majority of kids who present with specific reading disability have problems in, say the word cat without the first sound before they enter school, and this is the single best predictor of the first couple of years of reading. Once you get beyond 4th grade, it gets a little more complicated. So somehow what the brain is doing is reorganizing the semantics and phonology to create this kind of coherent triangle. And the best predictor of problems in building that triangle into the brain is problems in phonology. Phonological deficits are nearly universal in reading disability. But what's the underlying cause? Well, in grand rounds, I don't have time to go into all of these crazy theories. All of them single mechanism theories. And I'll tell you right now, dyslexia, as most of you know, is a heterogeneous condition and a heterogeneous population, and unlikely to have a single genetic, neurobiological, etiological pathway. In fact, there are probably many roads to Rome. We'll get to that in a few minutes. But theorists like single mechanism, we all do. My theory says this, and your theory says that. And here are some of the theories that are out there as to why dyslexic high-risk kids are at such an elevator. Oh, I forgot, you're filming this, aren't you? Sorry. I'm a walker. And I drank coffee, which is even worse. It's 8 o'clock, wake up. So kids who present have problems with metaphonology, with phonological processing. 3 basic things you often see. Metaphonological, that is phonological awareness, phonological working memory, and something called rapid automatized naming, the ability to take phonology and move quickly through input to output. But phonological. What is the cause of that? So many a medical mind would say, well, if there are problems in representation of language, that would make phonology very difficult to master. So perhaps the deficits lie in language cortex, in the representation of speech, less than ideally organized and specified, which would mean in preschool, we should see evidence that kids who are at risk for reading problems have problems with the mechanics of taking spoken language and representing it. So it's certainly a possibility. Others are not happy with the problem being specific to those brain systems that underlie speech and would prefer that it could be mapped further down into more basic sensory motor mechanisms. So there are theories out there that argue for problems in auditory processing, fast processing, Paul et al., slower amplitude envelope processing, Usha Goswami. So the argument is somehow there are problems in these systems. The data has not been universally kind to either view, but this is, I think, because it's so heterogeneous. Certainly, if you have problems in auditory processing, it's going to make phonological representations harder and therefore make building that triangle all that much more difficult. Because building the triangle, orth, phon, sem, involves changing the phonology so you can connect it to vision. This is really what goes on in brain. So there are also other theories out there about problems in access and retrieval, attention, and then low-level what's called noise exclusion. This is a kind of particularly sexy new one that's showing up in a lot of studies, where problems in brain of being able to kind of amp up some signal and damp down others seems to be operating at very low sensory motor levels in many kids who present with reading disability. And finally, an an intuitively attractive model that says, actually, like most other neurodevelopmental conditions, it's probably multifactorial, and there are probably many roads to Rome. So the cumulative idea that Hume and Snowling have put out, and which we're currently testing with our longitudinal data, is this. You can have any set of combination of risk factors, but if they make it difficult to create an efficient language-visual connection, you're going to get problems in becoming a 250 millisecond guy or gal. So the cumulative model is attractive, but why should I even be telling you this and then talking about the brain? Because every one of those silly theories is associated with a different hypothesis about the source of fragile circuit in brain. Let me repeat. Every one of those theories has a different locus to where the development of pathways is likely to be seen as different. If it's sensory motor, if it's specifically in language cortex, if it's in the attentional control systems, if it's in the white matter tracts that allow long distance connections. Every one of those theories makes neurobiological claims, and neurobiological research can be useful in discriminating them. So what is the brain basis of typical and atypical reading development? What has modern neuroimaging told us so far, in spite of the fact that it should be ashamed of itself for how much it overstates? Well, first of all, much of what we know about the reading brain comes from, actually a lot of it comes from Montreal, right? And the lesion patients over the years in the cases. This is the basic model that comes out of Geschwin's famous book in 1971. 100 years of lesion studies suggest a couple of things about speech and language. One, that the left hemisphere has an awful lot of biologic machinery that is specialized for speech, ranging from the perceptual organization of Wernicke's to the production or the output-related or motor mapping areas in supplementary motor into inferior frontal gyrus, and that these two systems work together to allow us to to talk and listen coherently. Now, reading, I forgot to mention this earlier, so I'm going to say this really quick. Reading and speech are like really different from one another in the following way. We are wired, and there's an awful lot of left perisylvian specialization for becoming competent listeners and speakers. So you don't need to go to school when you're a baby to discriminate the difference between cat and bat, because the brain has a lot of machinery that is ready to go. Now, that doesn't mean it's all in there. It needs ambient, stimulative environment. Moms and dads that talk to that baby all the time and allow those statistical learning algorithms along the perisylvian plane, this perception, production loops, to develop and coherently organize. But you don't need a lot of cognition to become a competent perceiver or producer of language. Children go through stereotypical phases of language output development, unless they deviate, that are entirely constrained by the maturation of the perception action systems in the brain. We are wired to talk and listen, but we are not wired to read. Surely, reading has only been around for 5,000 years or so. There cannot be brain areas for reading. So when Pugh starts putting up a bunch of pictures of brain circuits for reading, they're not reading circuits. What reading is taking a lot of other stuff, like language cortex, visual cortex, associative learning modules, attention, and giving them a new function, or as Standehan says, neuronal recycling, to build something that allows you to go from the back of the head into language cortex fast. Because when you're a skilled reader, you move away from vision and into language in a couple hundred milliseconds. And in order to build, so much of what we know about the reading brain comes from early work on lesions. For example, the importance of the angular gyrus. My first study, a publication, one of the early ones in this field, in 1996, shows you how new neuroimaging is, or fMRI at least, was implicating the angular gyrus, both in terms of its activation and its connectivity in dyslexia. And we know from patients, that if you knock out the angular gyrus, you will often get acquired dyslexia. So in the Geschwind, in the Wernicke-Lichtheim model, the Geschwind model, we have an important dorsal, sort of dorsal pathway involving the angular gyrus and supramarginal into language cortex. And if you knock out the inferior parietal lobule, you will get problems that can be very specific to reading, strikingly so. There's also a lot of cortex in the ventral cortex. Sorry, I'm very bad with this mousy thing. But because it's being filmed, I have to use it. So, wow, I hate this. But in fusiform cortex, there's also toward the occipitotemporal juncture, there's a lot of cortex that is also very important for mapping into language and becoming an automated reader, a fast reader. And one in particular that you'll see heavy focus in my field. And if you knock out fusiform areas, you will often get acquired dyslexia. So we know these areas are important. 100 years of lesion studies tells us what must be there. In a sense, lesion studies are the gold standard. But we also know the limitation. Because the brain does not operate with simple modules. So if you knock out one piece, everything is not the same. The brain is a nonlinear, self-organizing, dynamic, cooperative, competitive machinery. And in order to understand how it does language, reading, or twiddling thumbs, we need to understand its cooperative and competitive dynamics. And lesion cases provide a foundation, but modern neuroimaging techniques allow us to explore in vivo both the spatial with things like fMRI and temporal with things like EEG and MEG, organization of the language, the cooperative and competitive dynamics in the brain for language and reading. And since fMRI, which I use very heavily, gives excellent information on location and lousy information on timing, since it takes 6 seconds or so for the hemodynamic signal to peak, and EEG gives excellent information on millisecond timing, but lousy, well, arguably less good, not lousy, information on location. It doesn't take a degree in brain science to say we should marry the two. And most researchers these days that are doing interesting work on circuit and system are linking multimodal imaging. We do that as well. So after 100 years of lesion patients, what has modern neuroimaging taught us about, was Wernicke, not Wernicke, was Geschwind right? Well, of course. Reading looks kind of like this. Now, this is just a simple study of adult controls in my lab. It's part of a project where we're collecting data in 4 countries and looking at the overlap between spoken language and written language in English, Hebrew, Hebrew, English, Spanish, and Mandarin Chinese. This is English. Now, you're looking at the left hemisphere on one and the right hemisphere on the other, and in the axial oblique slices, left hemisphere is on right side, radiologic convention. What are we looking at? Well, we're looking at a very simple experiment. Pay attention for a minute and the rest of this will unfold. In this experiment, the subject is doing one of 2 things. Well, they're doing one thing. They're processing words, and they're pressing one button if it's a living thing, like horsey. And another button if it's a non-living thing, like wall. That's it. It's low level, simple. But the stimulus comes to eye or ear. And so now this is a map of voxels, which are these units of analysis in the MRI space, that respond either to speech only, and those voxels that respond only to the spoken word are painted red. And they live along the perisylvian plane and auditory cortex. And there are voxels that respond only to print. And those live where? In the back of the head. Duh. Okay, no surprise. But if you look at the green voxels, those are really muy importante. What are the green voxels? These are voxels. These are pieces of patches of cortex, pieces of brain, populations of neurons, whatever you want to say, that respond to both. These are multimodal areas that skilled readers need, you'll see in a minute, in order to become skilled readers. So if you are asking what's the reading circuit, it's yellow plus green. And if you ask what's the spoken language circuit, it's red plus green. And most of the brain in a literate person becomes, especially around temporoparietal inferior frontal loci, becomes, in a sense, multimodal. And this is really the key to much of what we've learned about reading when it succeeds and reading when it fails, the ability to create this kind of integration. And back to that triangle, the ability to bind orthography and phonology and reorganize speech cortex in important ways. So that's kind of what it looks like superficially. And there are, just for a minute, I want to just briefly touch on we've done 20 years now of nerdy experiments on priming, morphology, semantics, orthography, memory, attention, and we've penetrated these circuits and watched them change their dynamics and their connectivity. In general, what we've learned so far is that there are three sort of shamelessly large and underspecified broad regions that matter for reading when reading develops normally. There is a parieto-temporal frontal loop where, as you'll see in about 2 minutes, the brain does the job of actually learning to read, of making the triangle. So orthography is now going to get married into phonology, semantics, and morphology. And it depends heavily on the intactness of superior temporal gyrus, supramarginal, and angular loci interacting in a feed-forward, feedback way with inferior frontal gyrus. So the resonances that occur along the perisylvian but broadly extended cortex are critical in learning to crack the code, to becoming an accurate beginning reader. But if all goes well, there is a developmental shift when reading is working fine toward a greater role for a fast mapping set of routines in and around the occipitotemporal cortex. Okay, and this region has come to be known as the visual word form area, a misnomer at every level, but nonetheless important in brain. So what does building, so here's what I've been saying so far. Typically developing readers create this bound orthphon sem, and they build this sort of broad left dominant reading circuit in which some components, parieto-frontal in particular, play a very important role in learning. And when things need to become automatic, there is an important role played by mapping routines that map visual representations via the ventral pathway into language cortex. And the development of that ventral pathway depends upon creating green voxels, that is, creating cortex where print and speech co-activate and work together. Here's a study that looks at good and poor readers processing sentences that come either to eye or ear. And it's a complicated experiment, but the simple story is we have good and poor readers, good and poor comprehenders. This is an older sample of teenagers. And the only difference between them is their written language skills, their reading skills. And what we are doing is first we identify patches of brain where good readers, in general, have overlap. Those green voxels, again, print and speech hang together, and areas that are particularly sensitive to processing sentences, which turn out to be heavily involving inferior frontal gyrus, a sort of a dorsal aspect of Brodmann's 44. Okay? So those areas are like muy importante in skilled readers. And we test this idea, and I want you to grab this intuition, please. If you have become a better reader, then you've created more integration of natural language and these new representations. You've reorganized cortex in such a way to make it literate. And so if you're a better reader, we hypothesize you will have more overlap in these regions. yellow. If you're a poor reader, we hypothesize that you will have less modality overlap. And in this study, that's exactly what we found. So the higher the reading comprehension ability, the greater the convergence in cortex of print and speech. So this is kind of a nice illustration of this principle here. Previous studies indicate, our research indicates, we have one study of a pediatric sample, age 7, showing a very similar effect in superior temporal gyrus. This is another study of sentence processing extending into inferior frontal gyrus. But guys, simple story. The better the reading, the more you create this amodality. And this is an exercise in plasticity. It's not easy to take language systems that have evolved to walk and talk and listen, to make them able to tolerate and process a new kind of information. Now, very quick, this is not key to the thing, but you got to understand how kind of interesting this is. When you become literate and you get all those green, and you compare literates to illiterates who don't have green because they don't read. Remember, the green are these overlap voxels. Sorry, guys. It turns out that when you become literate, it changes your ability to do speech. So there's a very famous study of Portuguese illiterate adults. Half of the sample is literate, half literate, women from Portugal, brought into the Karolinska Institute. And the first thing you see is that when you become literate, you're actually better at doing pseudo-word shadowing, which has nothing to do with reading. This is where you say a pseudo-word that gets harder and harder, and I simply try to shadow in real time. And literacy has changed cortex in these ways that actually have an impact on speech and make speech better. So understanding literacy is not just understanding how speech predicts it, but how it changes communicative language. The literate brain is not the same as the illiterate brain, even when walking and chewing gum. Okay? And this is very important because it tells us what's happening neurobiologically when things kick in, when treatment works. We'll get to that if I shut up and move on. So increases in reading skill, as I told you, are associated with the development of fast mapping ventral specialization. One study we did early on, early as in 2002, it tells you what upstarts we are these days. We did 144 kids between the ages of 7 and 17 with a simple reading phonological analysis task. I designed it so that it could be age matched and appropriate. Half of the kids, 74, met criteria for, well, we're typically developing, and half met criteria for reading disability. But what we're asking in this big analysis is, what does the brain do as it goes from 7 to 17 and becomes automatic? And what does it do differently if it doesn't? And what we found, and again, left hemisphere on right, and this is the so-called visual word form area in ventral fusiform occipitotemporal cortex. Sorry, I can't make this thing work. You know where I'm pointing. This area is one of the few pieces of the typically developing kids' brains that the older they are, the higher the activation performing reading tasks. And that's shown in yellow. That correlation, positive, is yellow. If you look at frontal lobe and right hemisphere, the voxels are purple. That's a negative correlation. So ready? The bigger the age, the less you go there. So what we're seeing in the typically developing kids is the development of an efficient reorganization that allows some areas in visual cortex that are really good at fast pattern recognition to become literate. And what's not happening in dyslexic kids is that. So everything is positive. The bigger the age, the more they go everywhere. And frankly, nowhere, if treatment does not work. So keep that in mind when I get to my treatment slide. This is just showing with 144 kids this so-called visual word form area, so sort of down here behind my ear. The higher the automaticity of reading measured in this test, this is word attack, the higher the activation of the VWFA. Okay, so we know that what the brain needs to target is this kind of left fast mapping system. What about dyslexia? Well, we know a lot about what it looks like in the brain. And of course, I'm going to say in about 2 minutes that ain't good enough because it's not explaining, it's just describing. But here's what we've described in 20 years. That a large number of studies indicate anomalous activity and connectivity and gray and white matter volume, you'll see this on the next slide, in left posterior cortex, both in the temporoparietal and in the occipitotemporal. And children with dyslexia in the absence of treatment will tend to have very weak development of these fast mapping systems, and they tend to read with a very distributed circuit, including right hemisphere parietal and frontal lobe areas. So this is a kind of a compensatory response which gets you not to be a 250 millisecond guy or gal. So these are a list of some of the findings that are out there to date. We find unstable and reduced activation of left angular into fusiform. We find reduced functional connectivity. We were among the first, well, somebody beat us by 3 months at NIH. It drove me crazy, to actually look, because remember, brains don't work in pieces, right? So one of the nice features of functional neuroimaging is to be able to look not at activation, but connectivity. So the degree to which the activation of one region correlates with another. And when regions are working as a distributed circuit, activity is highly correlated. And when that circuit breaks down, the activation becomes uncorrelated. And we find poor correlation in left parietal cortex. And in my study in 2000, we also found that the dyslexics show higher connectivity in the right hemisphere. So there's clearly a kind of a compensatory response. In red here is something I don't have time to go into. I'm really going to get yelled at, although we're not that bad so far. I need to leave time for questions. But this is one that I just want to put up there as a tease, and I'm happy to take question on it. Most of 50 years of research on dyslexia has focused on theories of processing deficits, phonologic, sensory motor, rapid, blah, 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 attention. And they're there. What we haven't paid enough attention to is what every clinician in this room who's worked with reading knows. Kid comes in, bright, by definition, normal intelligence, comes in because dyslexia is orthogonal to IQ. Some kids with dyslexia are average or even below, and some are way, way, way above. It's just orthogonal. Kid comes in really bright. You teach them everything they need to know to build that triangle. They get it at 4 o'clock perfectly. They go home, they go to sleep, and what happens? Gonzville. This is really important. Learning disabilities affect learning. And learning is about offline consolidation and reorganization. I have an R01 that's currently operating now where we're looking at sleep-dependent, offline, hippocampally-dependent consolidation. Don't have time to get into it. But bottom line for clinicians, when you see kids who present with reading problems, they don't just show processing deficits. They will show phonological problems almost all the time. Not universally, but mostly. But they will also show problems in stabilization and essentially creating permanence to knowledge and to reorganization of circuit. Okay. Oh, I'm sorry. And very important, reduced gray and white matter volume across these left posterior systems. So volumetric MRI shows less gray matter in, for example, angular. And DTI studies show reduced FA, suggesting problems in myelination in this population. Now, for you medical people, doesn't that sound like, wow, that's better, closer to cause? Well, maybe yes, maybe no. Because the more you use piece cortex, the fatter the gray. So we can't separate cause and consequence. And in fact, all of this should be ashamed of itself because none of it is causal. What the current state of neuroimaging has provided us is an extraordinarily sophisticated neurophenotype. It's really robust, I must tell you. The stuff I'm telling you, we were among the early ones getting this in English, but it's been seen a lot. This sort of development of coherent learning and the fast mapping system and the failure to build it and the reduced gray matter and the shift to the front. This is pretty prevalent. But all of it is simply describing dyslexia at the level of populations of neurons in the same way you could describe it as problems in decoding pseudowords. Why this happens requires a deeper neuroscience, and that requires prospective longitudinal studies. And I want to take 5 minutes to go through the results of a current one, and then I'll end with a couple of slides on treatment, which is, of course, important, but you'll be able to get what you need, I think, just from a few slides on that. So we need to go beyond description and get at gene-brain behavior pathways that actually produce this heterogeneous but rather striking anomaly in circuit building. We are currently concluded one study of kids at age 7, and I'm going to show you two findings briefly from that study that look at genetics, neuroanatomy, neurochemistry, MR spectroscopy. We have a paper that just got in press yesterday that I'm going to show you on glutamate in dyslexia, and now I can say it with confidence because it's peer-reviewed. And also we're doing cross-language versions. The basic design of these longitudinal studies that I'm presenting, we're now currently in a new phase in my lab at Haskins, where we're doing versions of this starting at age 4. So we've pushed everything down into preschool where there's so much action. But this previous 5 years started basically at the age we thought we could keep kids to keep their heads still in the magnet. And at age 7, we did DNA. My colleague Elena Grigorenko at the Child Study Center is the chief geneticist for this. We did structural and functional MR at time 1. We did magnetic resonance spectroscopy and, of course, cognitive testing. We track kids for 2 years, and then we see what it was in those multiple measures at time 1 that made you either have a VWFA or not at the end of 2 years, become an automatic reader or not at the end of 2 years. A summary of some major findings, and again, I need to be brief. First of all, I'm going to show you this very quickly because there are speech and language clinicians here, but I'm going to do it fast. So a paper we published last year, or 2 years ago in Brain, showed that children who have early speech motor language delays, late talking, show anomalies in basal ganglia that are still evident at age 7. And they also, on average, are reading worse, and that replicates a number of longitudinal findings from different countries. We've also found that number 2 is just this integration. Number 3, a paper that we just published this year, found that when we look at the very youngest kids in our sample who are just learning to read, we find all the anomalies I told you about in left parietal and parieto-temporal, occipito-temporal cortex. But we also find anomalies when you're learning to read that are very striking in the thalamus and in frontostriatal pathways where they should be, because learning to read is learning, and learning depends on cortical, subcortical pathways. So what is emerging from that study, and I don't have time to go into it, is a growing understanding that the acquisition of that triangle, which results in this coherent and well-functionally organized left mapping, depends on the subcortical, cortical pathways. And I'm happy to take questions on it and talk about it later. And then finally, neurochemistry and genetics. So as far as late talkers, there are a number of studies in English and a very famous one in Finland that have shown that children who don't speak, who don't produce two-word utterances on time and are designated late talkers are at elevated risk for dyslexia later on. Now, not every kid who has dyslexia is a late talker, and not every late talker, of course, presents with dyslexia. But it is a risk factor, especially when coupled with family history, because dyslexia is heritable. So we had a large number of kids at age 7, but I had their histories. So in this paper published in Brain 2010, we simply, my colleague John Preston, whose first author is a speech and language PhD and a real expert at assessment and diagnosis, we looked at the kids who were late talkers, and the bottom line is we replicated the behavioral effect. So on average, late talkers are doing worse on reading. But when we looked at their brains, there was a massive, one of the strongest anomalies I've ever seen in the thalamus, in putamen caudate, and in, of course, Wernicke's area. So this cortical and the subcortical and cortical language, subcortical pathways showed major anomaly, and interestingly, showed anomaly for both listening, which they did perfectly well, and speaking. So this is some indication that when you're looking at very young kids who are presenting with language problems, that are associated with risk for building that triangle later on. You can see residual of that at age 7. If this is true, and if the basal ganglia is implicated in the failure to become ready to learn to read, then I should be able to look at 2-year-olds and begin to understand the development of this cortical, subcortical machinery as a risk factor. Because unfortunately, this study caught them at age 7. But I wanted to share that because it's clearly linked to what we know clinically, that speech motor development is a massively important risk factor for dyslexia. Okay, and then this is the spectroscopy. I'll do very quickly. So this paper, as of yesterday, thank you, reviewers. I love you. I love my reviewers. It's actually technically, they want me to fix a table, but we're in. And this is really bad because a lot of neuroscience people hate single voxel spectroscopy because nobody knows what the heck it is. Okay? Now, here's what it is. We take a very large voxel. That's it. My radiologist colleagues at Yale, Doug Rothman, has been a pioneer in interrogating this visual areas and being able to extract spectra for NAA, GABA, glutamate, and choline. GABA is hard to get in terms of MR spectroscopy, and it requires about 35 minutes of the kids watching a movie. So I had 75 kids at time 1 who not only did fMRI one day and cognitive testing and other things, but also watched a movie while we interrogated this voxel and tried to get the quantification of obviously the major inhibitory and excitatory neurotransmitters and other neurochemicals that matter to plasticity. And this is kind of what MRS data looks like. I'm sorry, I got to go fast now. There's been a previous study implicating choline and abnormal choline levels, choline to creatine ratios in children with many learning disabilities, including dyslexia. But there's never been a study of 7-year-olds learning to read. So you need to see the brain's chemistry not when you're 10 or 20, but when you're actually building the circuit. And this is the first study to be able to successfully get a very large pediatric sample. And we found and replicated that there's an inverse relation. In English means the higher the choline, the worse the reading. And you'll see this in a minute. We also found for the first time, because in dyslexia, nobody's looked at GABA and glutamate. In many other neurodevelopmental disorders, autism and ADHD, there have been evidence of elevated glutamate using MRS measurement, which has been associated with theories of hyperexcitability and noise. There's not been any previous study, adults or children, that has been able to extract GABA and glutamate in dyslexia. Now, this is the pediatric cohort. And what we found, and the R of this is not super strong, it's only about 0.38. But you can see that for both glutamate and choline, we have a significant group differences and a highly significant linear relationship. So the R square, which means the variance accounted for, is not massive, but there is an important link between overexpression of glutamate at T1, time 1, and choline. Elevated choline has been reported in many clinical populations and neurodevelopmental disorders and has been associated with, and again, this is, I got to go fast, abnormal myelination, abnormal cell membrane turnover, and a variety of other mechanisms. But it's frequently seen in neurodevelopmental populations. It appears to be a player in dyslexia. There's been 2 adult studies published before us in dyslexia found that. But you need to look at it at 7, and we found it. The glutamate has been found in many other populations where you find either neurotoxicity or at least hyperexcitability, and it's been seen in autism, it's been seen in ADHD, it's been theorized about, serum studies have indicated it in autism, and it suggests something that might well go to hyperexcitability. And I'm interested particularly in the glutamate, and I got to stop here, go to the last slide. Glutamate is important in my data set because the kids came back 2 years later and glutamate was still predicting. So the glutamate at time 1 and this essentially this inverse relation, too much glutamate, worse reading, predicted outcomes 2 years later. So what this tells us is that we might now have a penetration into biochemical pathways that down the road could obviously lead to experiments on pharmacological stabilization, manipulation, links to animal models, and other things. Okay, last slides. I'm going to skip genetics. Well, sorry. I got to show you this thing. This is a quick glimpse for you guys of a big literature. We were among the early ones looking at treatment. So I told you, typically developing readers go like that, and they get that triangle. Atypically developing readers in the absence of treatment end up in the right and the front. So what does treatment do? Are these left hemisphere systems fundamentally malwired? Or if you give good evidence-based treatment that goes directly to building the triangle, will you see some normalization, particularly if the kids are young? So this is a question of severity. Is dyslexia a mild neurological syndrome with noisy circuits and possibly noisy related to hyperexcitability, perhaps? At least, it's now out there. But is it possible that these things can stabilize? It's impossible that good evidence treatment can improve reading, and we've done years of that. So we worked with a magnificent treatment person. She's the star of this study, not the guy who designed the imaging. Benita Blackman designed this a fantastic 9-month treatment that your grandmother would use, because it is practice, practice, practice. 1 hour a day, 5 days a week, 9 months. Getting all of those elements, phonological awareness, decoding, rapid vocabulary development, routinization, fluency, even strategies for comprehension, but mostly decoding. So 9 months, we looked at 3 groups of kids. This was a big, expensive study, US taxpayer. Time 1, before treatment at about age 6, at the end of 12 months, after 9 months of treatment, and 1-year follow-up, which studies don't often do, to see if the gains were significant, relative to 2 control groups, typically developing and dyslexics who were getting conventional school treatment. Of course, I don't have a slide here, but the treatment group did better than the control group, and that was significant 1 year post. So like most good treatment, there were gains. But here's what happened in brain. We literally saw that in the left, all 3 parts of that circuit, there was a monotonic increase from pre to post to 1 year follow-up, and a decrease in front and right, which begins to look, this is real longitudinal data, and the treatment sample begins to show that reduction in right and specialization of the left. But there are many studies using evidence-based treatments that are beginning to show changes in those circuits. For older samples, 10, 11, 12, you see those increases, but you also see the compensatory areas increasing. It's not we had very young kids, and they essentially normalized. And we also have a bunch of studies that are hard to believe, but out there and well done, suggesting salient changes in gray and white matter measures when treatment is successful. So clearly, we have evidence of plasticity and response. But some kids won't respond, and so here's where I want to end, and I'll take questions. I hope we have a few minutes. What we have done with treatment is to show that when treatment works, the brain changes. Duh. And in a good treatment, 75%, 80%, if it's really good, are treatment responders. There's always treatment resistors. So we have a new program project grant with sick kids in Toronto and Georgia State and Haskins that for the first time in the next 5 years is going to be looking not at the difference between typically developing and RD brains, but the difference between kids who start out with reading disability, go through PHAST, Maureen Lovett's treatment, and then looking at what it was before and after that discriminates resistors from responders. Because the promise of neuroimaging to all of you is, and of gene-brain behavior measures, is exquisite sensitivity to individual differences and to heterogeneity. And the fact is, not everything works the same for everybody. So the next phase of treatment is to go beyond the gee whiz, when treatment works, the brain changes, and into what works for whom. Thank you very much, and I hope we have a minute or two for questions.
I know some of you have to leave. We'll just ask if the people in the Regent in Val d'Or or Royal Vic have a quick question for Dr. Pugh. I don't think so. Anybody here in the room?
Yes, ma'am.
There's a microphone.
Thank you very much. That was fascinating. I have a question relating more to the beginning of your talk.
Yes.
Is there a difference between the ability to read fluently out loud words and to read music fluently and perform it in a different sort of motor way?
Well, you know, there's very terrific people up in this part of the woods, like Robert Satori and others at McGill, who are doing interesting work on music and how it organizes in brain relative to language. I would say that there are intriguing droplets of data here and there suggesting that music training might have some transfer into some of what reading requires in terms of reorganization and plasticity, but it is not definitive by a long shot. But clearly we know if you map speech music and you map particularly the forward feedback circuits for speech, you will see a lot of overlap. And these are the same circuits that need to become plastic in such a way that they become literate accessible. So there are all kinds of perhaps superficial neurobiological reasons to say that these things should connect. There are, perhaps others in the room know about links to music abilities and dyslexia more. I have never been convinced by any of it. Is there anything on?
I knew about Satori's work as well.
Right. But as far as large studies that have sort of established, there's people even doing music as treatment. Oh, there's a terrific researcher at Northwestern named Nina Kraus, who does a complex auditory brainstem EEG. So this is microsecond timing, has found all kinds of anomalies in dyslexia, including instability at that level of timing that might reflect hyperexcitability and noise. Her work has been sort of writing the book on treatment, links between music and reading treatment. So if there's anything good out there or about to come, in fact, I know some of it is about to come out because I reviewed it a long time ago when it was a grant, I think it'll come from Nina's lab. And I would go to her website. She is sort of the leading person. Nina Kraus, Northwestern. Yes,
Dr. Auger.
Dr. Auger.
I'm sorry, this is going to have to be our last question, but if you want to come and speak to Dr. Pugh after.
Thank you very much. That was very interesting. I work with refugees and immigrants who come from other countries, and often the parents, mothers usually, are illiterate. And I just wonder if there's any difference in reading disabilities in adults that are learning to read first their maternal language or when they're learning to read a foreign language, if there's any data on that.
There is some data. It is, I'm going to have to, how can I make this really quick? It's a very complicated and rich area. We have some grants that are looking at biliteracy and bilingualism ongoing right now that are addressing this. But I will tell you, we have found one interesting thing, that the age of acquiring the second language in its literate form, whether two languages are acquired early or later, and whether it's the dominant or non-dominant language, has very profound effects on how the circuits organize. We published a study a year and a half ago. I'm happy to send it to you. I'll give you my card on Hindi-English bilinguals and how kids who were learning Hindi and stabilizing it and bringing English in later were quite different than kids who had learned them together. And so this is sort of the link between this, and that just complicates everything when you deal with immigrant populations, native, indigenous, native language L1, whether that language is being lost or preserved. It's a very complicated area, but an incredibly rich one for research. So I don't have any simple answer to that great question, but I'm happy to pass on every reference I have that is going into the grant that we're currently conducting to address that. Anyway, sorry guys.
I'm sorry we have to finish so you can all go to your other work, but thank you very much to Dr. Pugh for this.
Thank you very much.